For video number 3 in this motion tutorial series, I want to dig a little bit deeper into how you move components around in the different study types. So we were introduced in the last video, there's animation, basic motion, and motion simulation. I'm going to use each of those study types to show you these blocks basically separated by a certain distance and then coming together as if they were moved, or perhaps they were falling together with gravity or pushed by a motor. We'll start by creating the first one, which is an animation. Now in animation, you've got a couple different ways of doing this. You could just use drag motion, where you basically just grab the part and move it. And when you let go and animate it, it's going to go ahead and move that thing along from point A to point B. But very rarely do we want things to just randomly go from place to place. We want them to move in very specified, specific ways. So I'll undo that. And what I'm going to do is add a couple of mates here to kind of line them up, because I want them all to kind of be in a stack, in a line. And so what I'm going to do is add a mate to this face. We're actually doing a multi-mate so that it goes to here and here. Now before I get there though, I get this dialog come up. And this dialog should do one of two things. It should help to remind you that you're actually in a motion study, which if you didn't realize it, you're in trouble now because you've been making changes in the motion timeline as opposed to in the model tab. But the other thing it's saying is you're moving this in the model by creating a new constraint. Do you want this to be the initial constraint, or do you want this to be a change from the initial constraint? I want this to be the initial. So I'm going to say yes every time this pops up, because basically what I'm doing is assembling my model specifically for the motion study. And I'll show you kind of what that looks like and how that differs from what you might otherwise normally see. So there's my first mate, and for the second one, I'm just going to do this. And so all I've really done is just set the tops and the fronts coincident to each other, and now these things, when they move, go back to times 0 just so you can kind of visually see, when they move, they'll move in a straight line. Now, it's important that you know that the mates are added at the motion line timeline instead of in the model tab, because they don't exist in the model, they do exist in this motion study. So if you create a mate and you want that mate to be globally available to all motion studies, you really want to create it in the model tab. That way it'll automatically show up in any motion study you work on. And that's obviously the way most people work whenever they're putting an assembly together. But let's say that I want these to behave in very different ways in each motion study. In that scenario, I can go down to the motion study and add them there, and they will not apply back. As long as you understand that's what's happening, it's not going to trip you up. But you can understand how adding a whole bunch of mates and with the motion tab visible, and then going back and trying to figure out why your mates disappeared on you could get very confusing. All right, and by the way, the same thing goes for deleting mates. You can delete mates in the motion study that were imported from the model, and they will not delete in the model. They're only going to delete here in the motion study. So the next step I want to do is I want to create a distance mate to basically cause these things all to fall together. So the first one is just a distance mate from here to here. These are 1-inch blocks. So I'm going to start them out with a 1-inch gap. And this one too will go 1-inch distance mate. And that's our starting point. And then I want to come out to 1 second. And this is where I want my first one to go down to 0. So they're kind of just collapsing down to 0. And then at 2 seconds, we'll have this one collapse down to 0. So edit and go to 0. But I don't want it to kind of change speed as it goes. I want them both to be moving at the same speed initially, and then I want the second one to close its gap. So that's where I'll grab this 1-inch gap and I'll move it out. Just basically drag it out. And what that's going to allow me to do is specify where I want it to be. Now, notice when I did this, something really odd happened. Notice my change bar is gone. What I've effectively done is turned that mate off at time 0 by dragging the initial point forward. Now, you can expand that out and decide whether it's the distance or the suppression state of the key that you're actually changing, because there's multiple levels. That key represents both the suppression and the dimensional value. But basically, if I just unsuppress it here, it turns it back on, and now it's active through the whole thing, and it's only changing its dimension at this point. All right, so calculate this again, and it kind of looks like they just fall into place. Now there's an immediate start, an immediate stop. There's no acceleration allowed at any point or specified at any point. Animation is very much does only what you want it to do and nothing more. If you want to kind of clean that up a little bit, you do have a few interpolation modes. Interpolation modes allow me to ease in or ease out. So for example, if I do an ease out on this one, what it should do is quickly start moving and then slowly slide in. That looked really weird. Let me kind of change this view a little bit. It's like it came in for a really soft landing. If I flip that and say ease in, what that's going to do is it's going to start accelerating and then snap down to the end. I'll do the same thing on this one and see what that looks like to make it as realistic as possible. And you can kind of see that like herky-jerky, click, 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 clunk, clunk, clunk motion that we got going on there. That's caused by this animation frame rate. So if I click the little gear here for the motion study properties, that frame rate of 8 frames per second would really only be appropriate for a really long, slow movement. Let's go ahead and change that to 100 frames per second because we're only doing a couple seconds. And now you can kind of see it kind of goes. Again, it's not very realistic though, because at the beginning of this, that ease in really doesn't work very well. So we probably need to change this interpolation back to linear. And let's see what that looks like. So we're kind of going together, boom, the first one hits, and then the second one comes in and hits. Is it realistic? No. Does it get the point across? Absolutely. But that's what animation is all about. All right, so that was in animation. Let's see what it would look like if we switched over to basic motion. This should give us a lot more realism with respect to the actual movement caused by gravity, interactions between the parts, etc. So when I calculate it, immediately it throws up this message. And this is one you want to know about, and this is one that causes a lot of people a little bit of grief when they're starting out. This study is using key points, which is these key points that cause it to move based on input specifications. But key points are not supported in the basic motion solver. The assembly may not move as expected. And in fact, when it calculates, you'll see it doesn't move at all. Because you can't just say, go from here to here, trust me, the math works out. In physics, the math needs to be worked out by gravity, by Newton's laws and things like that. That's what the solver is giving for you. You're not telling it where to move, you're telling it what's going on, and it'll tell you where it ends up. So in order to make this work, what I'm going to do is get rid of these distance mates. Because quite frankly, they don't work in basic motion or in motion analysis. So now I have these things and they're all floating and they're all mated still. So the mates are still being used, but I need some other way to propel these things forward. That's where I might come in with, let's say, a gravity. So with a gravity, I might say I want to do a negative x gravity. I could also do it with some of these other elements. We'll start with gravity first. And I know that gravity is going to work very quickly. So when I calculate this, I'm expecting those things to just disappear off the screen, and they do. So if we look at just the first couple of time steps, do you see how it just immediately flies past? All right, but I don't want to change gravity. I don't really have the law to do that, but I can change how long this study solves for. So what I want to do is basically I'm going to do a Control Q, which kind of clears out any history here, and I'm going to say I only want to look at 0.3 seconds. This very, very top bar, this very top key point and that very thin line, that's where you define how long you want your study to run for. So I've done that, 0.3 seconds. Now that's going to go very quickly, but what I've set my playback time to is 5 seconds. So it'll scale the speed so that it always takes 5 seconds to see what happens through the whole timeline, regardless of what the actual time units are. I'm going to calculate this, and what it's doing is basically saying the frame rates aren't quite where they need to be. It's a little too slow. I'm going to say no, and I'm going to see what it looks like. And you'll notice at 100 frames per second, I have very few frames here. It's just kind of clicking through real slow, herky-jerky. So it recommended maybe doing something more along the lines of 267. Now notice the frames per second is actually in a different spot here. Basic motion. Let's do 500 frames per second. See what that does. I'll calculate it. And we still fall through, but we have a very realistic acceleration caused by gravity going on here. So in order to make them stop when they hit, I've got to define contact. So I'm going to say I want to do contact between these components, and I don't have very many components, and they're all really simple, so I'll just grab them all and say, okay, those all need to have contacts. And it goes through and it stops. So it's a very accurate, very realistic reference. Now that one does bounce a little bit at the end. That bounce is caused by the way the solver is calculating interferences. Now we're going to go into a lot more detail in contacts, the way contacts are solved, but suffice it to say, SOLIDWORKS Motion is cheating a little bit, and instead of using flexibility in the components, it allows those components to interfere with each other very slightly. And so the amount of interference sort of corresponds to the amount of force required to push them together, which would kind of represent a little bit of a squishing effect caused by that stress. Like I said, we'll get into the details a little bit later, but that's basically how that works. All right, so this, if I go back to animation and run it, look at this gravity and the solid body contact. They're suppressed. The animation solver does not solve for force, gravity, things like that. The basic motion solver does, and does a very nice job. Let's turn the gravity off. I'm just going to delete it. And let's see if we can use one of these other types of study elements. So let's do a force. Apply a force there, flip it around. Force doesn't matter too much. Value force doesn't matter too much. Click OK, and the force is suppressed here. So again, we've got 3 different solvers. Each one uses different types of elements. Force is only relevant in motion analysis. So we can't do that here. We'll delete that and we'll try something else. Let's do a motor. A motor is another great way to move things. So we'll do a linear motor on this face. Constant speed of 1 inch per second. And let's see what that does. Okay, again, our timeline is not quite suited for the job we're in here. So this 1 inch per second means we'll probably need about 2.5 seconds to get it all done. And that means we don't need 500 frames per second. We're probably closer to about 100. Let's see what that looks like. First one comes along and hits it. Second one comes along and hits it, and it stops. Now, that's what we expect. That's what we want. That linear motor is behaving very much in the same way that the distance mate is. And in fact, you've got a lot of options here for whether you want to go a specific distance, you want to oscillate, throw in maybe some, calculation formula to specify the motion. But just by saying I want it to move by a certain distance or a certain speed, it just goes along. But when it hits a resistance, it stops. And this is true of almost every study type Whenever you give it an impossible situation, such as an unstoppable linear motor reaches a fixed body with solid body contacts, it will go ahead and stop. There's a hierarchy to which one stops which one else, and we'll talk about that a little bit later when we get into redundancies and things like that. But suffice to say, if it's not moving, odds are you have too many mates, everything's bundled up or bound up somehow, and you probably need to loosen things up to get it to where it can actually move. All right, so basic motion we've got figured out. We can use gravity, we can use a motor, those work really well. Everything else we would have to go up to motion analysis for. So I go up to motion analysis, I apply or I calculate this study, and what you're going to see is it pushes, but then it squishes. And if you actually wait long enough, you might be able to push that all the way through the block. And what's going on here is it's trying to approximate material properties in these blocks. Now, if I go into solid body contact, previously all it said was use contact groups and tell me which components you want. Well, now in motion analysis, we need to give it additional information. We're going to go into a lot more detail a little bit later about what exactly is going on here. This dialogue requires quite a bit of exploration for getting good motion studies done. But if I just go ahead and calculate it now, steel on steel, it tends to be a little bit stiffer, but it ends up kind of in the end. Actually, look at this. It bounces off the first one and then smashes together and then squishes. Now, why does motion analysis and basic motion, why are they separate if they're using a lot of the same elements? And the answer is because there's some very specific things that you can do differently in motion analysis. In addition to taking into account the flexibility of the components, you can come in and create a result plot. So for example, I want to know what the force is on the motor, the total magnitude of it, for this particular linear motor. And I want to know what that is over time, and it'll automatically show me over time what's going on. And if I hit play, you'll see that the force is going way up right here, and that's what that big string along is. Let's actually take this and drop it down. I don't care about what happens at 2 seconds when they all make contact. I want to zoom in just a little bit more into that area where everything is moving. And it looks like probably what's going on is there's no mass on any of these parts. So that motor force, or that linear motor, is basically not doing much of any work. If I scale it up, you can actually see there is a little bit of a pop there where it hits, but it's next to nothing. And that's fine. We're going to get into something with more realistic numbers soon. But motion analysis allows me to do that. But that's also where I could get rid of the motor and instead do something like a force. Whoops. Go back to time 0. Pay very, very close attention to that. So I'll add a force, this direction, click OK. Now I can run the same study, but instead of a motor, the force causes it to go a little quicker because of the value of the force, and it smashes it, and then it doesn't quite force those materials to squish quite as much as the motor does. So we'll explore more of that later, but it's the main thing I wanted you to get away from this lesson is motors, mates, drag motion, forces, gravity. Each one of those is appropriate in different contexts. And so you gotta ask yourself, do I want to show movement? Do I want to create an environment where motion is possible, which would be basic motion, where you have the kinematics are a little more accurate? Or do you want to take it a full step further and actually go into motion analysis where you can get data readouts and you can get more sophisticated analysis? Choose wisely and understand that you may have to rebuild your study or adjust how it's done if you change the type of analysis. We'll see you again in video number 4.